So just to kind of get my bearings real quickly. So when we left off yesterday, Njoki had given this, first of all, good morning, everyone. Welcome again. And to the third and final day of this training. So when we left off yesterday, Njoki had quickly given, an extensive overview of our work, the ensemble of the things that we've been working on pertaining to dryland mapping and monitoring, which is kind of what our group focuses on. And I think, if you recall, she covered a variety of, she covered so many things that may be pertinent to some of you attending this training, and as well as other ancillary work that we do. And the general theme is basically we want to improve mapping of vegetation and resources with a bit of focus in drylands, because like she mentioned yesterday, one of the problems we have in the Earth observation community is that drylands tend to kind of be disadvantaged, in the sense that there's a lot of great work that's done within the Earth observation community, but less attention is paid to fine-tuning those applications for drylands. So after her presentation during the last 30 minutes, I tried to walk you guys through a sample code for and I believe I had shared this repository. Let me know if you didn't get that repository link yesterday. This was the repository that we were working on. Just one second. This would be the LAI partition. Yes. So I tried to walk you guys through this slice, a vertical slice of how the partitioning would work. And I think that is where we stopped with a few questions. And I said that what we'll do today is that we would make a demonstration, because the script I showed you yesterday was just to grab the leaf area index data from Google Earth Engine and run it through the algorithm that Njoki developed, and how to go from the aggregate leaf area index to the partitioned leaf area index, and which is what this script basically does. I would copy let me just grab the link and post it in chat in case anyone didn't get this. Okay. So this is how you go from an aggregate leaf area index to partition area index. And then something I wanted to mention before we move on today was that there was an important question about woody cover towards the end, and I just wanted to make a note that I realized after that we were using the wrong layer for the woody cover, because the woody cover is an important ingredient, and I'm going to go into more details about mapping woody cover shortly. And so the layer we used was from a previous iteration, which kind of underestimates woody cover, but I later figured out that I wasn't using the most recent one. And if I go into my assets here, which is where we have the most data, this one, yes, West Africa 40 cover, this should be the most up-to-date data, and we can replace that. And if we replace that in the script, basically replace this one that I was using, which was at 100 meters. Now this is at a 40-meter resolution. We just replace that in the script. We run it, it should still work, but we should notice a significant improvement in the woody cover, where it is no longer underestimating as previously in certain parts, particularly in the drier areas. So anyway, I just wanted to make that note there. So I've adjusted that. And then so getting leaf area index itself, it's fine. But quite often as a pastoralist or as an end user, you are interested in what's the value add. How do you actually apply it? How does it make sense? How do you go from the aggregated or disaggregated leaf area index to something that is meaningful for you in terms of like drought monitoring? Now, this data that you're seeing here, we are just processing 5 years of data because it is very fast to do that in Earth Engine. And I wanted something that would run live. So this is our analysis that we left off yesterday for those who had already left. So you can see the aggregate leaf area index, that's the plot there. After you've smoothed it, then these are for 3 different landscapes. The top one is the savanna in the northern fallow. This is in the eastern Senegal where you have woodlands and shrublands, but it's still largely deciduous. And then, of course, the forest area where the leaf area index remains high. And then this is what happens when you do the partitioning. So as you can see now, the woody cover, it's acting a bit more typically now because, we'll switch it. The red line is basically the woody where we expect the max potential leaf area index for derived from tree canopies. And then the orange is the aggregate, and then the blue is the herbaceous. So how do we go from this, which is largely a scientific output, to something that is, a manager can really use? So I'm going to make you a demonstration for something. I'm going to show you a demonstration that we did. This is not yet derived for West Africa, but we've done this already for East Africa. So if you have access to the repository and you go to the scripts that says LAI partitioning drought monitor East Africa, we have something like a dashboard that shows that how we can use this data for a meaningful application for drought monitoring. Yeah, sometimes these codes, the centering tool doesn't work as it's supposed to work. So, okay, so this is Kenya, this is East Africa. And what we did was that this is using the MODIS. So for this to work, we had to process at least 10 years of leaf area index data. So we processed 10 years of leaf area index data from 2013 to 2022. This was towards the end of our AST. This was part of our AST3 project when we were working with the Eastern Southern Africa Hub. And we already performed the partitioning and kept this as an asset in the Google Earth Engine. And then we computed monthly values, monthly aggregates, and then now from there we can compute anomalies. So if you, for example, if you select, let's take 2019, for example, and then we select the month of May, which is the peak rains in Kenya. So we have the partitioning. On the left there, you have the partition leaf area index, the woody on top and the herbaceous. You can see the contrast there as we do after you do the separation from the aggregate and the woody. It's gonna take a while to load because it's computing the anomalies on the fly. So give it a couple of seconds or minutes. But on the right, it's going to show you the anomalies, which are basically the z-scores. And what it means is that it would take the month of May for that 19 and compare it with all the values for May for our entire time period. And then it would use the z-score to establish whether the conditions are relatively good or relatively worse compared to typical. And this is kind of a straightforward way to establish that a particular year. So this is particularly in the context of what we are working on now, which is livestock insurance. This is one way of establishing that, okay, this year there has been enough stress to forage resources to warrant, maybe payment or to trigger payment. Okay, so this is I chose 2019 because I remember that we're coming in a bit of a drought. And that's why you're seeing all the red there. If we fast forward to 2020, seek. But anyway, this gives, you can play around with it. The code is there. And what you can do is that you can also, if we've processed the data for the rest of continental Africa, we can actually create something like this though. But it's just that for the purposes of this training, we don't yet have, we have pre-processed data for all of continental Africa, but not available in Earth Engine. Njoki has been processing most of the data outside of Earth Engine. And we've been trying to see if we can recreate the application in Earth Engine, but Earth Engine has its limitations, particularly, and it's not designed for it's not really designed for operational use. And which brings me to another key point. I think Phoebe is here, or Kevin, I don't know who else is here and can comment on this. We are actively working, I think, with the SEO to have this data available in the rangeland decision support tool, which is the tool that was inherited from the Eastern Southern Africa hub that used to be developed by our colleagues in Eastern Southern Africa. And so we are hoping that that would be the end goal for this data, to have this data available in the RGST. And by the time we have the full continental product available there, then it should be possible for anyone, whether in West Africa or Southern Africa or any other part, any rangeland area in Africa should be able to use this and hopefully have a similar dashboard like this to demonstrate to be able to use this for forage.
If I may jump in, please. I think Emil had his hand up.
Yes, go ahead. Sorry, I wasn't paying attention.
Yeah, no worries. Thank you, Julius. I guess two things. One would be, well, first, I guess one would just to mention quickly that at least from the Science Coordination Office side, I think that we find your use of Earth Engine pretty nice, innovative. I, for one, of course, we've talked, you and I, Julius, but I really appreciate that, you've made your code available in these, curated repositories, which then make it, easy for other people to access. I think that is nice. And I also think that, that's like an opportunity for other PIs to also kind of like learn from your example of, hey, here is how to kind of package up some of the analysis that you're doing. So just to say thank you for the great work, and thank you, of course, for being available to share, what you've been doing for East Africa with our friends and colleagues in West Africa. And then the quick question I had, you mentioned that Njoki processed the data outside of Earth Engine. Just kind of wondering why that was. Back to you. Thank you, Julius.
Njoki, is Njoki in the room?
I can.
Do you want to answer, Njoki?
Yes, I do. First of all, I want to recognize the effort Julius has put in to make this palatable for so many people, because a lot of times we do the science and think it's usable, but it's not. But Julius has tried to translate this into a graphical user design where people can access that data, but also try to assess some of the challenges with the data. And I really appreciate that. But I will not.
You're breaking up.
I am? Oh. Yeah? Can you hear me now?
Yeah, I was able to hear Njoki.
Yes, I don't know whether it's my. Oh, I guess it was my end then. Sorry. Sorry. Apologies.
Anyway, there are several reasons why we wanted to keep it to the native tiling system that is generated and data available from the MODIS data. That is one reason. But also, as Julius indicated yesterday, Google when he's trying to implement some of the scripts, there are so many steps that are incorporated into the script, which he might not even be able to put all of them in place. I know he's done a really good job on this, but Google Earth Engine has its limitations, and so Am I?
Yes, go ahead.
No,
Go ahead. Sorry,
please go
I
ahead.
think someone was.
Yes, so we wanted to have an interface where people can access the data, but at the same time have the best outcome from the processing chains that we implemented. And so when we were doing this work, and Julius has also said, downloading data from Google Earth Engine is a nightmare. It is not meant for getting all the data in and downloading that data. So getting it out has become a big challenge, even for the people in NASA headquarters who are trying to like navigate and see how best they can use these fast processing capabilities of Google Earth Engine. But at the same time, how do you get that data out once you do the processing? And so we kept these two separate platforms so that if someone wants to download that data and interact with it, then it's possible for them to. Otherwise, if we just left it on Google Earth Engine, it is not going to be a nightmare, because some of the smoothing and pre-processing steps are not also accessible within Google Earth Engine. And Julius, help me if I've missed anything.
No, you're right. You're absolutely right. I'll just add that. Well, you started this work, I don't know, 7-8 years ago, and you were working on your desktop in Python. That was before Google Earth Engine. So before Google Earth Engine came, you had already pre-processed and even published the first version of this data several years ago. So when we started the Survey AST3 project, Njoki was actually working at ILRI and trying to push this. So we've always maintained that hybrid and a desktop approach, which can be cumbersome, but at least you have control. So we have the data here at New Mexico State University, which Njoki processes on the HPC cluster, and which we also recently pushed to the Oak Ridge National Laboratory archive. But like we said, we are working with the SEO and also our colleagues in East Africa to see if we can make this a big part of the RGST tool, which in the event, we don't know. I know that Google Earth Engine is not going away anytime soon, but in the event, for some reason, we have issues down the road, we know that that is a reliable option. So, yeah. Emil, did you have any other comments?
No,
Okay.
no, thank you so much for those clarifications, Dr. Njoki and Dr. Anchang.
Yes.
It was just useful to kind of like, the why. I wasn't, criticizing. It was just kind of interested to know kind of why the specific workflow. And definitely also, know that they're still, a big part of the Earth observation community who, it's kind of like, whether you want to use a fork or a knife. And so it's not like, one way
Right.
is better, et cetera. It's just we as scientists, we all have different ways that we want to store our data, et cetera. And so thank you so much for that background. And again, I think that's really useful for our West African colleagues to kind of be aware of in terms of their own navigation of this space. So thank you so much. Back to you, Julius.
Yes. And so, like you said, Emil, if the code being here, I have an active document that I'm working on that I'll hopefully share with you guys, if not by the end of today, but hopefully this week. I already shared the link to the document, but I'm still working on it live. That would include all the links to all the repositories, and even future changes that I will make to this repository, you'll still be able to see it and access it as long as you keep that link. So that should be fine. And anyone who wants to run this analysis locally can still create this application because the template for the code is still here. So, okay, so let me just wrap up on the leaf area index. So you can see here, if you clicking on a specific, so this was 2018, and it's flipped from red to blue, which means that, we had strong positive anomalies in 2018. And you can notice that the anomalies are more significant for the herbaceous, and that makes sense because even when we have a mild drought conditions, the woody part component doesn't really get influenced as much as the herbaceous. A slight dry here, the herbaceous reacts more strongly than the woody part, and that kind of makes sense why you see the woody anomalies tend to be non-significant or less profound, but the herbaceous anomalies can be strong, flipping between red and green, and that is kind of useful. And this is like for this small blue area that you see here, that's what this data is printing. It's a specific ward in Kenya, which is kind of like small forage management unit, small administrative unit, which provides kind of like a good scale for monitoring forage resources. Okay, so any questions on LAI before we kind of pivot?
Julius, can I ask a quick question? So
Yes.
up to now, you've been using Modus LAI. Is there any plans for like VIRS LAI, etc.? And then also, I think there's a question from Glory in the chat.
Okay. All right. Let me just check that quickly. Yes, Emil. Actually, right now we are working on transitioning to VIRS. In fact, one of the big key part of our current project is that transition. And Njoki, I believe, has already performed the necessary calibrations between VIRS and Modis. And so it's just a matter of reprocessing. And well, we don't have to reprocess because we've processed the historical data, but going forward, we should be able to process using the VIRS. The two products are consistent enough that it's straightforward. And actually, the example that I showed yesterday and the one that I showed earlier, the vertical slice, that is actually using VIRS, not Modis. So yes, and the question,
Julius, just to chime in, if you let me, about the VIRS data, this is also been implemented because of our current EST. We have done this for the Horn of Africa countries, and we have been able to implement VIRS partitioning just for the Horn of Africa. But if and when we get all the necessary woody cover, updated woody cover, we will be implementing this for all of Africa. So people should be on lookout for this.
Yes. And by updated woody cover would be an example of what I just showcased earlier, the improved woody cover for West Africa that I just uploaded. And so that would warrant us to go back and reanalyze, particularly the historical epochs. Yes. And yes, the question in chat about the code. So this is part of the repository. I don't think I sent it by chat yesterday. So I would have to send the link. Let me get the repository and post it so that people can permanently get it here. But you can click that link to go directly to this script. But let me just share the repository again. It's public users. Repository. How different is the use of NDVI compared to LAI in crop growth anomaly detection? I will take a stab at it, and Njoki can come in to if I miss something pertinent. So one of the key value adds of value additions of this product is the separation of the woody and the herbaceous. Now, if you know your crop area and you've clearly defined it, if you're sampling at the level of field or farm, and you know that that's okay, everything in that pixel is agricultural, then obviously you can use NDVI to monitor your crops. But at scale, where you start to get mixture of different land cover types or mixture of different vegetation types, herbaceous, woody, or even a farm area that has a lot of trees around or mixed in a savanna area, you start to have the problem. NDVI starts to break down because it is now just like aggregate LAI, it is an aggregate index that does not give you that separation. Now, LAI itself is more useful, even without the separation. LAI itself is more useful than NDVI because LAI is quantitative. It's basically telling you the total of leaf area, amount of leaf area in a field. Now, this is relevant to forage because animals eat leaves, basically green leaves. But for agriculture, it might just be relevant in terms of, it might not be so, that it might not be that critical to agriculture where, you're more concerned about the health of the crop. And in which case NDVI and LAI can be just as good as each other. But the real value addition that we are offering here is the separation of the woody, so that you know that in this landscape, we have removed the part that is due to woody plants, and you can basically track what is happening with the herbaceous.
As if I can chime in too. The question is, how different is the use of NDVI compared to LAI in crop growth anomaly detection? And I will answer this in relation to what happens in Africa. Most croplands, like this would be very limited, and I did talk about this when I was doing the presentation yesterday about some of the challenges of using these vegetation indices when you are monitoring drought, or in the context of index-based livestock insurance or crop-based insurance. Or index-based crop insurance. The challenge with most African countries is that crops are rotational, and so you don't find the same crop being planted this season compared to the next season, and so that variability might influence the way you look at the anomalies. So depending on what you want to look at, I think most of the models that I've seen in monitoring crop production and drought anomalies in cropped areas, it's not necessarily using NDVI or LAI vegetation indices, but it goes beyond that. I hope I answered that question properly. But in terms of the rotational cropping that happens, it becomes quite difficult to capture the anomalies in cropland areas across Africa.
Okay, thanks, Njoki. Okay, if there are no other questions, I think we can pivot now to talking about mapping woody vegetation. So what you can see on my script there is a different repository, and I have named it Survey Training 2024 Woody Cover Mapping. And these are basically, I have so many other repositories that I use for this, but I was able to fine tune and clean up some of the code that I think it's relevant to share and can demonstrate all the key steps. So I'm going to post that code here. But again, like I said, these links will be available to you these links will be available to you in a kind of a user guide document that we'll be drafting, but I'll also send them along with the presentations that Njoki did yesterday to Glory, to disseminate. So if you are able to access that repository right now, you will have the link, you will have this repository. If you click on that link now, you should be able to access this repository and with the different steps. So to kind of give a background to this, for those who have been following our work, ever since we started working with SERVIR several years from AST2, mapping woody vegetation has been a big part of that. And that was mostly because, first of all, as a research lab here at New Mexico State, our group is focused on drylands. And that was because, but also because it became very clear very early on that existing global, existing products, by products I mean Earth observation products, maps, remote sensing products, do not do sufficient justice to capturing the dynamics of woody plants in drylands. And if you've worked in drylands, you know that, for example, the global forest cover product is not very useful because it's designed to capture closed canopy forest, or a specific definition of forest which has to do with trees of a minimum height and certain coverage. And by the time you start to zoom in drylands, things start to break down, and it's ignoring all these things. But we know that there are a lot of trees there's a significant amount of trees and woody plants in drylands that play an important role in not only in ecology but also in pastoral, in the dynamics of socioeconomic dynamics of pastoral livelihood. So what I'm trying to say, what I'm rambling here is that we've tried over the years to improve maps in drylands pertaining to woody vegetation. And what I'm about to demonstrate to you would be a vertical slice to create a simple, straightforward map. Now, there are other products. The recent years, by recent I mean the recent 3 to 5 years, have had significant improvements in this domain. So it's important that I mention them. One, we have the Copernicus Global Land Cover product, which also provides layers for tree and shrub cover. And compared to the previous products, like the Global Forest Cover or the VCF product, it does do a better job. But we've recently published a paper when Njoki did an analysis to assess for bias in the estimates, and we've realized that there are still a lot of lingering issues even with that product. And one of the things we noticed is that it flips the other way around. It goes from the VCF underestimates and ignores trees and drylands, and then the Copernicus data overestimates trees and drylands. It's just overestimated. Then also there's a fundamental issue with the methodology, because they initially do a land cover classification at the final scale, and then they just add, so their percent tree cover, for example, is an aggregation of the classes at the final scale, not so much like a straightforward empirical estimation. Now, the other approach, which is more recent and more cutting edge, is the use of AI and deep learning. And if you are familiar, you may have, maybe you've heard of, the Sahel tree crown maps, which have been derived by the scientists at the University of Copenhagen, Dr. Martin Brandt and colleagues, Dr. Jim Tucker from NASA, where they have basically tried to process very high resolution data for the entire Sahel. Not only the Sahel, but I think they have even extended to the point whereby we are no longer looking at canopy cover in terms of a total pixel and an uncertain an estimate per pixel with certainty, but with uncertainty, but so much as actually delineating individual tree crowns and deriving biomass estimates from that. And it is great. The work is phenomenal, and we really commend that. But there are a number of issues with where that approach is. While it is not yet quite the what's the saying? It's not yet quite the holy grail of of being able to give us very accurate and reliable or useful data. First of all, high resolution data is really difficult to get, and even though it's more abundant now than it's before, it's difficult to process, and it takes an immense effort. And then secondly, the data that has been produced so far lacks a temporal component, which is important to many of the use cases, right? If you are looking at long-term degradation or even short-term removal of trees and shrubs, you need a temporal component to that. If you're looking at seasonal variations or drought, you need a temporal component to that. And because to get the full coverage that they have now, they have to mosaic data from over a long time period, and that kind of loses that. So those are the two mitigations, but it is phenomenal, and it's definitely the future. I hopefully will get to a point. So where would we fall? We fall in kind of like in the middle ground. We think you can get high res, but not incredibly high res, but you can still maintain a certain level of reliability, still using the traditional method of an empirical approach. Basically, you get plot data you have reference data that you've measured accurately at the level of the field. You have a statistical machine learning model that matches that data with satellite indices and then predicts a layer for canopy. And that is where we are. And we've believed that a lot of the work that needs to be done is just to be careful about the calibration data you use. I think that's essentially my experience of working on this in the last 5 years has come. It's not so much the machine learning method that you use or how fancy it is. It's just being careful with the data. What's the quality of your reference data? How do you sample it? How careful were you with selecting the indices that you use as predictors? And and then how do you estimate your uncertainty at the end of the day? So I'm going to start with reference data. So when I started working on this, when I started working on this 7 years ago, I first created woody cover data for Senegal. And back then we had our colleagues at CSE provide us some field data. Now the problem was that field data was only a few, like 100 and something points. And if you've used machine learning model, whether it's random forest or gradient boosted regression trees, you know that that's not nearly enough. So this began to push me towards what are the other ways we can get reference data to support models that we use to estimate woody vegetation, woody crown area. And so eventually that led us, yes.
I'm sorry to jump in here. You have not granted access to this code. Some of the lines are throwing up errors.
Oh, okay. Let me do a quick check.
All right. Thank you.
Let me just do a quick check. Can you tell me which script?
The one you are showing on the sample select.
Okay, all right. Let me see.
What? They might or they might not, because they said that they're.
Let me just make sure everything. Just check everything. Okay. Yeah, that's everything.
Yeah, Julius, it's saying your ISA calval, your cover, your XVARs, your not DEM2, but your tree mask. So these specific ones, ISA calval, cover, XVARs, and tree mask, these four are not shared.
Okay, all right. And the truth is that some of those layers are not even relevant to this script. That's why.
Okay.
All right, just doing that quickly. Tree mask. Yeah, that's different. Right. Maybe if you refresh, hopefully the changes have taken effect. Okay, I think I've shared whatever needs to be shared, and I've removed what is not relevant to the script.
Yeah, it's working now. Thank you, Julius.
Okay, all right, thanks. So now the sample select script. Okay, so I lost my trend there. So anyway, my point was that field data is not enough. That the short of what I'm saying is that you rarely have field data in the abundance. It is the ideal data. It is the reliable data, like what CSE does, where they go out every year or every 2 years and measure crown areas in the field. They measure biomass. That is perfect data, but you hardly ever have enough of it to be useful in certain contexts, such as using machine learning. It can be useful for field-based monitoring, but if you're trying to do machine learning-based monitoring at scale, it won't work. So that means that we had to find alternatives, and the alternatives was to use high-resolution data. And even though, like I mentioned before now, that people are trying to map all of this stuff at high-resolution data over large areas, but that has caveats. We may not be able to get high resolution data that covers an entire area, but we can have high resolution data for selected sites. And if we have those high resolution data for those sites, those can provide us the necessary data. Most people in this, am I correct to assume that everyone here is familiar with Collect Earth?
Collect Earth Online? So.
Yes, okay. So yes, so initially we started using Collect Earth 2, and we do have some data, several thousands of points. I need to make a mental note to share that data too, that we collected using Collect Earth Online, because we thought that was a quick way to get a lot of data, but we have had to abandon that route too, because Collect Earth is very good for land cover, but not very suitable for tree cover, because tree cover is a continuous estimate. You're trying to measure the percent tree cover in a plot. Collect Earth is, you're labeling points to see if it touches a particular land cover type or not, or a particular tree. So it doesn't quite work in the same way when you're trying to use it for estimating tree cover. Also, if the underlying imagery is not so good, then you end up with a lot of uncertainty. So we've had to pivot from that. So we had to go back to the traditional way of getting high resolution data for different sites that have been sampled. And we were able to do that with the NASA, as NASA scientists, we have access to high resolution data. This is commercial data, so it's not freely available, but as NASA scientists, we have access to high resolution data that we can download for selected sites. And this is what we were able to, this is where we ended up and said that, okay, we can get high resolution data for selected sites and use them. Basically, we get those high resolution data. So in this case, we have several dozen images collected all over continental Africa. We kind of try to make the selection so that it covers the different biomes and the different precipitation gradients. And we individually process this data. Now, if you try to classify resolution data individually, it's going to take you weeks or months. So what we do is that we combined unsupervised classification with human interpretation. What we basically did was that we did an unsupervised classification initially using a neural network approach. It's a neural network approach, but it's still unsupervised. And then we follow that up with the visual inspection to see how well the classification did to recognize the tree cover class, because our interest here is only the tree cover class. And based on that, we created this little code that I did here. It's meant to follow up a visual check. So from this code, I have already extracted over 3,000. If you see here the table, the code that says the asset that says table, you can see here there are over 3,000 points. As you can see, those little dots there, those are the different sites across Africa that we've collected high resolution data from. And within those, each site, we've collected multiple points. And so we have over 3,000 of them. We can use that in our model, but we can also follow up to validate and make sure that all the data we are using is good quality. And so this is why I created this code. So if you select, let me choose one that I know works reasonably well. So you select a plot like this, it overlays the classification that we got prior to this, and then we can do a visual check and confirm. And you can tweak this to different, you can tweak this for a different analysis. You can tweak this for land cover, you can tweak this for different. But here, I'm just trying to do a visual check as a human expert to confirm that it did a decent job of capturing the tree class within. Now you can see there's a slight offset. That offset has to do with auto rectification. It doesn't mean that there's anything wrong with the classification. It simply means that there's a slight there's a slight shift in the auto rectification between the base layer in Google and our classified data. And we just give a validation of the classification results. 2 means that it's good, really good, we can use it for validation. 1 means that it's slightly underestimating or slightly overestimating, but it's okay, it will still be very useful, we don't have to discard it. 0 means that the entire thing is just the classification breakdown at that point, and we should just discard that plot. And you can do this, and you can go through thousands of plots. Maybe if you have 5,000 plots, you can end up with 2,000 plots that are very high quality. And because what I've learned is that the quality of the calibration data is more important. You can plug anything into a random forest model and it will give you good results. But as long as you have bad data to start with, you will be an uphill task from there. So I just wanted to show that that is how we arrive at the kind of continent-wide selection of samples that we will use in our canopy cover model. And this is actually the second iteration. I had a previous iteration whereby you actually saw all the unsupervised classes and you choose the best unsupervised classification before creating this mask. But I've over time refined that to just produce to follow the unsupervised classification with a supervised classification that produces the relevant class we are interested in. And then we just do a visual check of the relevant class and see if we reject the plot or we accept it into our data. So here is not so much, I'm not so much sharing a tool here that you can just use. It's the principle of how you can, do some quality check on the data that you're using. So you could have your own small UAV image in your local area. That is fine. You could have your aerial photos or aerial image in your local area that you trust, and you can process that, in ArcGIS or some tool that you use, and you can derive this land cover class. But this is just a way of saying that if you have so many thousands of, because we could not do a handcrafted, accurate classification of all these images of 40-something or 50-something images that we have all over the continent. So we did a general classification, but we can go through and select areas that we think have done a good classification job and reject those that have not done a good classification job. Any questions so far? Okay. Now, the next step in creating your satellite, creating your woody cover data is to produce the satellite indices that would be useful as predictors of woody canopy cover. So you have your reference data, which would be your independent variable in your model, and that's what we just looked at how to select. So this is where we combine old school statistical modeling, mechanistic understanding of the landscape, savanna landscape, but with the idea of throwing everything into a black box and see how it works. So for this, I would open this document, which I think I also shared yesterday, and kind of go through. Right. Okay, so this is a work in progress training guide document that I'm working on. I think I shared this link yesterday. Let me just share it again. It should be available to the public. Share. Apologies. Let me open this directly on the desktop. Apologies, just give me a second. All this identification.
Hand up, Julius.
Yes.
Emmanuel, can you answer your question?
Okay, so thank you very much. What I wanted to ask was okay, first year. At first just what we were doing was we were using Open Forest Collect. That's also one that collected. And then from other research that we did, we had to create the systematic samples first in ArcGIS, and we tried that one. Also, in Open Forest Collect, you can generate your samples from there. You know, it's interlinked with Google Earth Pro, which is open source for us. And we did that. We attributed our samples with our tree cover class. No, that is no tree cover, very low tree cover, medium tree cover, and high tree cover. So with every class, there's a percentage that we assign to the samples. After doing that, we went back to ArcGIS. Then we converted those samples to a raster image. Now the issue is the con of Google Earth Pro is that we have variety of years, so you know we can't really get a definite year that we want to look at. Let's say we want to look at 2020, we will not have that because there's a variety of years. So looking at what you have done right now with G, I was wondering, did you imported your samples into, did you pick your data, your training data outside and imported them into G, or how did you go about it?
Yes, good question. So the samples that you're seeing here were originally derived from high resolution images. So like I mentioned, we access the commercial basically the Maxar worldview data directly. And because I was trying to create a woody cover map for the more recent years, so I knew exactly what to filter. So the portal, the Maxar portal that we have access to, I was able to filter that data for that time frame. So all the images I collected were from 2022, for example. And because we've had so much high resolution data in recent years, it's easy to find an abundance of images within a certain time frame. If you start to go back a bit further back, say 2010, 2005, because they weren't collecting too many high resolution images back then, it starts to become a bit more scanty. But when you look within recent years, you get it. But like I mentioned, this is a commercial platform. So I selected those data for the time frame. So my calibration data corresponds to the time frame I'm trying to create my map for. And then I did the initial processing outline using ArcGIS and Python to derive the masks. And so why don't you see me import? Because one of the restrictions of the licensing for the commercial data is that we cannot make the data available in a public. So I cannot, for example, put the high resolution data in Google Earth Engine. So what we did was I processed it outside of Google Earth Engine, and then I imported the masks, the three masks that you see there, into Google Earth Engine, where I can now do the calculations of I can visualize it, because Earth Engine gives me this easy way to create a UI tool that I can use to visualize the plot and see if it's a good data. And then I can automatically calculate the percent, the precise. So like you mentioned, you guys were giving it a label. We are not giving labels here. We are actually trying to calculate the precise percent canopy cover within the plot. And that is what this approach is about. It's about getting actually measuring the percent canopy cover precisely, not so much as a label to say this is high, medium, and low. So yeah, so we got we process the high resolution data outside of Google Earth Engine because it's commercial data that we cannot make publicly available. But the derived product from it, which is the classified product, we can share that, and we are able to put that in Earth Engine, which is what I'm using here to create my samples. Does that answer your question?
Yes, it does.
All right. Thanks. But like I said, if with this script, you can access even the data that I have. The data that I've shared if you see in the script, you see the asset is there, and I think it's publicly shared. So you should be able to copy it to your own script and use that data. But this is more about me showing a way of doing things, not so much as giving you something exactly that you can use. So quickly, since we need to get on time, the next step after making sure you have your reference data is to get the satellite indicators. And this is informed by science, informed by theory, but it's also informed by a general understanding of how body cover works. So what we are using here is a combination of, this is where I guess this training, our work coincides with the main theme of this training, which is the SAR optical fusion. I'm sure, Xiaojing showed you a lot of cool things on Monday about, combining Sentinel-1, Landsat, and Sentinel-2, for a couple of different applications. We are combining them here, but not in the same manner. Basically, we are just using them to derive a bunch of indices that we will use as predictors in the model. So straightforward empirical prediction of body canopy cover. So from Sentinel-2, we get what we call optical reflectance, right? Your visible near infrared, shortwave infrared bands. And Sentinel-1, we get, of course, the radar backscatter. So we combine those two. Without going into so much details, you can get that from this write-up. Share, copy link, sorry. Let me put the link to the document here. It's on OneDrive, so I don't know whether it opens directly like in Google. Yes. It's on OneDrive, so I don't know whether it's open directly like in Google. No, sorry, I think I copied the wrong link. Sorry, copy. So, okay, you see the training guide doc. Again, it's a document in progress. I'm just opening in case I'm just posing in case you want to follow or kind of read through it and scan through the methodology. But this document is still a work in progress, and that I'll hopefully share with you guys, at the end of the training. So we get all these indices from Sentinel-1, Sentinel-2, and we combine them, and in total we have about 29 indices. What these indices basically do is that they capture the average conditions in the landscape. So we have average backscatter, average modified vegetation indices, average reflectances, but we also capture seasonality. So mean, max, median. We also capture the dry season indices. The dry season is because in many areas, the dry season is where you get that distinction between woody plant material and non-woody plant material. So if you capture the dynamics in the dry season alone, that can allow for making that contrast, because what we really want to do is to capture that gradient from dense woody cover to sparse vegetation, which is mostly herbaceous or bare. And all of these indices are supposed to do that. So it's kind of all explained here. And we do this, and this is what this script does. If I can go back to the script I was looking at. Okay. So derive predictors by AOI. So this script basically does that. I'll quickly go through what the script does. So we have our inputs here, Sentinel-2, multispectral, level 2A. So this is the surface reflectance product. And it's kind of nice to know that it's just one harmonized product. Now you can use Landsat for this. Just so it's important to know that you can use Landsat, especially the Landsat 8 and 9 for this, because a lot of the bands are similar. You just have to know which bands mean what in the code so that you can replace it. The reason why we went with Sentinel-2 is that we started working with this 5-7 years ago with Sentinel, when Sentinel-1 and 2 were like a hot thing, and we've maintained that consistency with it. But also there are certain advantages. The 10-meter resolution, working from the base of 10-meter resolution is very useful when you're trying to capture as much variability and as much of the fine patterns in the landscape. Even though we don't produce it at 10 meters, but starting from that point of view of 10 meters and 20 meters helps it. And then lastly, the temporal resolution, because you can get Sentinel-2 every 5 days, and you can get Sentinel-1, I think it's every 11 or every 12 days. That is much finer than what you get with Landsat. So you can imagine that you are trying to create this satellite indices from so many images. if you have enough images, even if one is cloudy or has gaps, you can quickly fill it up because you have a higher cadence. So that's one of the reasons why we still prefer Sentinel. But you can absolutely do this with Landsat to replace Sentinel-2, and you still fit a model that still comes out looking reasonably well. Now, what you cannot get from Landsat is the radar backscatter. And the reason we have radar backscatter is that this method traditionally relied only on optical data, but radar has proven to be very, very powerful when you are trying to discriminate with the vegetation in dryland, because radar is not sensitive to the, it is sensitive, but it is less sensitive to the seasonal phenology that you get with optical data. So an area that has dense tree cover, even if it's deciduous, the radar backscatter should still be significant in the dry season, whereas in optical data, you will not see the difference between that area and a dry grass because it's no longer green. But also cloud cover. Radar offers better stability because you don't have the issues with cloud cover, so you are more confident about the indices that you compute from radar. So when you combine radar on its own is not enough, but when you combine it with optical, it significantly improves the ability of your model to accurately predict body cover. So this script basically does that. I've designed it so that you can just specify an area. So this is somewhere in Senegal, just a small bounding box of about 1 latitude degree, 1 latitude, 1 by 1 latitude degree. And what it does is that there are a couple of functions here. This is a terrain correction function. This is an addition. So this is not like what we call radiometric terrain flattening. That you cannot do with data in the Google Earth Engine. But this tries to mitigate some of the artifacts you get in mountainous areas. The good thing is that we don't have this problem much in West Africa because we don't have significant areas with terrain that impact radar. And which is kind of nice to have, but when you start working in other areas such as East Africa, Southern Africa, South Africa, radar can get really problematic because of the terrain, the artifact. So this tries to mitigate that. It basically performs an angular, based on a paper that was published recently by some guy called Andreas Horat. It basically performs an angular slope correction on the radar, and then this is to mask the edges, to kind of eliminate some of the banding or the stripping effect you get, whereby the illumination imbalance that will be to normalize the data so that you have this effect in the mosaics whereby one scene looks different than the neighboring scene. So we try to mitigate all of that, and then this is a function which we've created just to process Sentinel-2 because there are many steps that go into Sentinel in processing Sentinel-2 to derive the different indices. So if you go to this script here, s2indices.js, you would see this is basically a script model or a function that you can import, and that would all you need to give it is your filter criteria. So by filter criteria, you give it, let's say, the time that the date you are filtering for, the area, the bounding geometry you're filtering for, and then you specify the max cloud probabilities so that it can perform cloud masking. And it does a couple of things. It masks the edges, masks clouds, masks cloud shadows. Then it adds a series of vegetation indices. The SWE21 is the ratio of shortwave infrared 2 versus shortwave over shortwave infrared 1, which is a very important indicator of not only moisture conditions, but also dry conditions and also soil conditions. So it's very useful in the model. M-Survey is the vegetation index we're using. You can use NDVI, you can use EVI. In the context of machine learning models, it doesn't really matter. Most of them will just perform as well as the other. NDWR is the water index, NDRE, and if you go back to the write-up that I have here, in this table, I kind of explain the relevance of all these indicators so that I don't spend so much time. So you can read that for the relevance of all the indicators. And so this script does that. So if you run this script and you define your area, it will create you an image with 29 bands, and those 29 bands are basically your predictors that you use in your model. There are so many of them, but it's some of them are just statistical. So after you create, it goes through, okay, it takes data for 3 years. So because I want to produce body cover data for 2022, we filter data from 2021 to 2023. Why do we choose 3 years? Why don't we just choose 2022? The reason being that you are trying to create the most stable and reliable indicators. We don't expect woody cover to change rapidly, particularly in savannas. If you're working in a forested area and you're trying to look at deforestation, obviously this approach doesn't work because you can have someone go in and clear the forest, within a matter of weeks. And so this approach doesn't work. But in savannas, we generally don't expect that type of dynamic. So what we do is that we cover a 3-year period so that we can have enough data to create matrices or indices that are stable. So when we create our average NDVI, it's based on a 3-year data. When we create our average radar backscatter, it's based on 3 years of data. We first do it on a monthly basis to create a monthly mosaic, and then based on that, we create broader statistical composites, average, minimum, maximum, and like I said, like I mentioned, so we have all of these are the different indicators. You can see the VV mean, that's mean of VV backscatter, mean of VH backscatter, blue reflectance mean, green mean, but we also have the minimum values to kind of capture and the maximum values to kind of capture that in triannual variability. And then we also have the dry season values, which is where we take the same indicators, but what is their average condition value in the dry season? And then we have the amplitudes for the vegetation, which is the min minus max. And so all of this is, so we'll have our reference data and we have our satellite data. So what do we do now? We can build our sample, our data now for our model by simply extracting. We take our plot measured canopy cover and we extract all these values for all these 29, and we have basically our table, which is so the next script is the model calibration and validation. And this is where we've extracted. So those points that we talked about, we've extracted them, as you can see here. So you can see every point now, each plot that we had a woody cover measurement, now we have all the values for each of those predictors, VV, VH, all that, all the 29 predictors that we created. And then now we can run a simple machine learning model calibration and validation. So this script here basically does your simple training and test set split. So basically, based on you reserve your data, a certain percentage of your data, say 10%, 20%, 25% for validation. You fine tune your model, and then you compare that with the validation, and then you reserve another. So you need 3 sets of data. You need one small data that you keep and you never touch it until you are happy with your model. That will be called your final validation data. Then within the other data, you do a cross validation. So you can use bootstrapping techniques, and you can do all. You don't have to do this. And this is implementing the algorithms in NetEngine. You can export this data as a CSV and take it to your R or Python scikit-learn and do your modeling there until you're happy with the model. The problem is that it's kind of tricky applying, but I think there are tricks out there where you can learn a model outside of Python, outside of NetEngine, and then apply just the model and transfer maybe the learned model. I think there are tricks out there. But what I usually do is that because I'm always using gradient boosted regression or random forest for this, I just come back and replicate as much as I possible the same model in NetEngine, and it's usually very close. So this script just does it separates a test sample and it runs, it trains the data on the other sample, on the large sample, and then it performs a validation on the test sample by comparing the prediction. So this is, you have to define your variable list, And then this function here does that train test model. And we've specified our model here, which is where in this case, we are using our model here is the so our model here is the tree boost. So in Earth Engine, so you see, I've played around with. You can play around with different models to see how they work, and you compare the RMSEs. And so what it does is that you can see here. So this is the test sample RMSE. Test sample is more useful than training sample because it shows you how the data performs, how the model performs on data that it did not see. We have a high RMS. We have this is the training RMSE. So this is the training prediction. So this is not very useful because it's based on the training data. What you want to see is this one. This is what you want to see. This is more realistic because this is how it performs on test data that was not used to train the model. As you can see that we have a very good R-square of almost 0.8, even though our RMSEs are about, we can do better with our RMSEs about 16%, but I've come to learn that the RMSE is not as important as making sure you have this line. So this line here, you want it to be as close to the one-to-one line as possible. Because RMSE just tells you about the spread. Okay, you have uncertainty, and which is normal to expect from a machine learning model. But the closer you are to the one-to-one line, the more you can trust that, broadly speaking, your estimates, correctly reflect what you're hoping to get from the landscape. And that's it. And when you fine-tune this is not the final version of this model. I just use this for demonstration here. When you've done this and you've fine-tuned it and you've gotten your RMSE maybe down to 12% or 10% or something you're happy with, you can go now and apply your prediction. And when you apply your prediction, basically take the model classifier and predict against the image that you created from here, and then you get your woody cover. So the last thing I want to do is to show you a demo of the data we just created for West Africa. And basically, it's the 2022 data, 2022 woody cover map for all of West Africa that we've just created. And this is like a nifty. If you go to the script called demo, let me make sure that all these things are shared. Actually, no, this is public, so that should be fine. This is public data, so it should be fine. Let me know if you are able to access this script or if everything is being shared properly. And this is like a simple visualization of the woody connected cover we've just created. So you can see that the scale there from 0 to 80%. We cap it at 80%. The reason we cap it at, we haven't capped the data at 80%, but the reason I like showing this up to 80% is because when you predict woody cover from, especially in machine learning models, there's always a bit of a bias. So it slightly underestimates at the higher end and then slightly overestimates at the lower end. So 80%, if an area, when it has a prediction of over 80%, you can be sure that it could be even up to 100% sometimes. But that's kind of how it is. But those of us interested in Drylands are not concerned about that because we rarely get up to 80%. We are more interested in what's happening in the 0 to 40%, in the 0 to 50% range. And if I kind of zoom in here in Senegal, when you zoom out, you don't see the patterns well. And this is at 40 meters. When you zoom in now, you can start to see some of the patterns a bit more clearly. Because it's at 40 meters resolution, which is fairly high res, you can see it peaking, and you can show this with a background just to see. Remember, this is percent canopy cover that is being predicted by the model. And then, so you can see how it's picking some of the dense areas, particularly in the riparian zones or the riverine vegetation. But also, if you zoom out, the gradient from the fellow in the north, where you have tree cover, although it looks bare, but when you start to zoom in, you see it's trying. It is trying to pick the. Sorry. So it's trying to pick. So these areas are, you see, there are trees there, and this goes back to a point. I think I forgot who asked the question yesterday. with regards to charcoal monitoring in Ghana. So it's important that we make the distinction between cover and density. So you can see a lot of trees in an area, but it doesn't mean that the canopy cover is great because these are just small shrubs. So you could zoom in and say, oh, there are a lot of trees here, but if you actually measure the canopy cover, it's like 50% or less, or even less than 50%. So so this is kind of, and if you remember that our RMSE, our root mean square error is in the order of 10 to 15%, it's about 15%, then you know that, okay, you can say give or take 10 to 15% roughly, which can be impactful in the drylands, but the important thing is that we are picking the fine patterns in the landscape. And if you click on a particular location, because I try to overlay some admin areas, then it can spit out some statistics for you. Again, you can customize this. This is the second level administrative area, Lingere, that's northern Senegal, and it's telling us that on average in that area it's about 89%. It's like 10%, 11% woody, 89% non-woody, which kind of tracks compared to somewhere further south, like in the Casamance region, where if we click on any area here. Now, this also tells us that a lot of these southern areas, although they should be forests, if you zoom in, you see a lot of agriculture, a lot of degradation, a lot of deforestation. So our woody cover, when I previously did this work a couple of years back, we did not have enough training data in these regions. And what we were doing is that we were overestimating and not picking up some of these fine landscapes. Because a lot of agriculture here can get confused with dense forest because during the growing season, it's all green. But now because we fine-tune our model and we have higher quality training data, we are able to pick the mosaics and even identify areas where the forest is being broken up, versus area where you still have preserved nature. You can see that it can go from very high, full 80%, 100% cover down to less than 10% cover just because of the agriculture and all the activities that are going there. So I will end by making a comment. Now, what I've demonstrated to you is an approach to create one map of woody cover. Now, I talked about temporal scaling earlier on. So how do we go from there to create a temporal time frame? Now, the global forest cover product is available, correct me if I'm wrong, the VCF, it's annually or it's epochial. So we have what we call epochial woody, and even the Copernicus, they are trying to produce a layer every year. I think they stopped after 2020 or 2019. So epochial woody cover is a big thing that we want to do. And even for our LAI partitioning, our leaf area index partitioning, how accurate this data is critical to how that the leaf area index algorithm works. So there are different ways you can do this epochially. You can go to this is 2022. If you wanted to create another image for 2017, for example, or 2019, you can either repeat all of this process for that. So you have training data from that time period, you create your images and you fit your model, and that's cumbersome. But when you don't have historical data, what do? You have to rely on good quality satellite indices. And right now, the limitation we have with Sentinel is that Sentinel, unlike MODIS or Landsat, Sentinel do not yet have the products. They do, but they are not available in Net Engine. That provides you that high level of normalization where you can train a model in one epoch and apply it. And that is something we are actively working on. One of the things we are working on right now, and I hope to complete in the next month, is to say, okay, I have all this training data from 2022. I can filter those plots to select only plots where I know that there hasn't been a significant change. And I use those plots to train a model, and I can apply that model. I can use those plots in a different epoch. So even though the plots were made, the measurements was in 2022, it should still apply in 2015 because I know that the conditions in that plot hasn't changed in the last 10 or 20 years. So that's one way to do it. The other way is to do normalization. So you can use like pseudo invariant features to the indices you create at a different epoch, you make sure you normalize them. You can do a regression between those indices and at a different epoch to normalize the data. Because the problem is that you can't just create this, I can't just take this model and go apply it on a different epoch without doing some sort of normalization. So that is what we are working on, because the next step is for us to create the epochial products we can. And then also lastly, Sentinel starts from 2015. Actually, good Sentinel data starts from 2017 because they don't even have surface reflectance data going back to 2015. So that limits our time frame. So in this case, you might have to delve into Landsat. And I'm happy to hear that Landsat has, and I recently just discovered that Landsat has a BRDF corrected product, adjusted product in Earth Engine. So going back to 2013, so that can be useful. The problem is otherwise you have to go with MODIS because MODIS has a 20-year product, the NBAR product that can give you stable in the satellite measurements going back 20 years that you can apply the same model throughout the time series. But then you are losing the resolution. You're going up to 500 meters, and at 500 meters, you are no longer picking some of these fine patterns. So there's a lot more that we would like to cover, but I think I would like to stop here. And what can happen is that going forward, we can, if there are